Hello everybody, in this lecture we will be solving 1990 IMO problem number 6. Here is a view of this problem. We would like to show that there exists a convex 1990 gon with two properties. First, it should be equiangular, and second, the lengths of the sides, we have 1990 of those sides, are 1 square, 2 square, and so on, all the way to 1990 square in some order. So there's a very important result in T2's Mathematical Olympiad Treasures book, page 51. It is listed as Theorem 2.40. Let me start by stating and proving that result. So let me write the following lemma to begin with. So let A1, AN be real numbers, and also let the nth root of unity be epsilon. So epsilon is just cosine 2 pi over n plus I sine 2 pi over n, the nth root of unity. So given these, so we have the following result. If the sides of an equiangular polygon, a convex polygon like we have in our case here, have lengths a1 all the way to an. Recall that these are all real numbers, but in a given order. In this case, in counterclockwise order, then we have this very nice, cute result: A1 plus A2 epsilon plus A3 epsilon square plus all the way to A sub n, A sub n epsilon to the power n minus 1. This sum happens to be equal to 0, and we would like to prove that. Okay, so consider the following. Let's focus on the case. So consider the case n is equal to 6. Let me just show you the logic behind the lemma, and then the proof is just almost immediate actually. So how to draw an equiangular polygon? All you do is you can just start by just drawing a regular polygon, n-gon, in this case a hexagon. So let's assume so that looks like a polygon kind of. Okay, so this is our regular hexagon, and all I will do is I will chop off some of the sides parallel to it, so like that probably, and maybe like that. So this side is parallel to this, and that side is parallel to this side, and now I will just remove each of these. So do you guys agree? So because of corresponding angles, each of these angles are equal to 2 pi over 6, right? So and so this is an equiangular polygon, and moreover, let the sides be in counterclockwise order, like in the statement of the lemma: A4, A5, and A6. These are the side lengths, be careful. So what we can do is the following: we will give a twist to this shape and think of vectors. It is obvious here that as vectors, if you consider the vectors A1, A2 with the given directions, for instance, if this is where the vector is pointing to, this is where this vector is pointing, and so on, right? So all these vectors, if added, we know vector addition very well, because it is cyclic, it is equal to 0. So the sum of all these 6 vectors is simply equal to 0. But how to make sense of it? So how can I express these vectors each in terms of the roots of unity here? For that, for instance, one thing you can do is, as T2 mentions in his book, if this is the real axis, this is the imaginary axis, and let me change the color. So I have A1 here, right? So what I will do is I will just put A1 like that here, and this is the length of it, but this is actually, you can think of the vector as well. So this is the vector, and then A2 is the next guy, which is it has a 60-degree angle, so probably like that, A2, and A3 will be the next guy like that, A3 shorter. A4 is in this, yeah, A4 is this direction, sorry for that. Yeah, A4 is this guy here, and then we have A5, which is this, A5, and finally A6 would be something like that. But long story short, because each of these angles are separated by 60 degrees, it's not difficult to realize that, well, A1 is just the vector A1 is just A1, right? Because it's exactly on the real axis. But A2 is simply, the length is A2, the length of this vector. But then, so I'm analyzing the whole thing in the complex domain, obviously. So it's just A2 times epsilon. Epsilon is a rotation operator, if you will. So it is the sixth root of unity. It will, when multiplied by a another complex number, it will rotate it by 60 degrees, basically. Because A2 is a real number, it was on the real axis, so we have rotated it 60 degrees. In a similar way, A3, so we have A3, A4, and so on, A5, A6. So A3 would be simply A3, the vector A3 would be A3 times epsilon square. And similarly, A4 would simply be A4 epsilon cubed. This one would be A5 epsilon to the 4th power, and this one is A6 epsilon to the 6th power. So, long story short, what I'm trying to say is all these vectors now can be replaced equivalently. I can write it as A1 plus A2 epsilon plus, and recall epsilon is the 6th root of unity, all the way to A5 epsilon 4 plus A6 epsilon to the 5, so that's equal to 0, and that proves the main result, right? So we just did it for a particular case, just to show you the picture, but you can easily generalize it, obviously. Okay, so having known that, now we can start with the following claim. So I'm going to carry this problem into the complex domain, this geometry problem into the complex domain, and in that domain consider the permutation of the following numbers. Let n sub 0, n sub 1, all the way to n sub 1989 be a permutation of the following numbers, right? Of the numbers 0, 1, all the way to 1989, and they also satisfy the following thing. And so let me write that down, and then let's discuss this. N sub r squared times, oops, sorry for that, times cosine r epsilon plus I sine r epsilon is equal to 0, where I should explain what epsilon is here, where epsilon is the 1990th root, sorry, the angle, sorry, so where epsilon is 2 pi over 1990, and as a well, okay, so just to clarify, this follows from de Moivre formula. Remember that if epsilon is equal to the 1990th root of unity, then epsilon to the rth power is simply CIS. So when you are taking the rth power of this whole thing, it's just r times 2 pi over 1990. Okay, so that's our expression here. But do you guys, does everyone agree now that this directly follows from the lemma, right? With the only exception that we do not know the actual ordering of these numbers, so of these numbers n0, n1, and 1989. So it's a permutation of this, and we need to find it. So we need to find an algorithm that would allocate these numbers into this expression here. And when you plug in 0, 1, 2, 3, and so on, so you'll get, for instance, as you plug them in, so you will get 1 plus 0, which is 1 squared, and then when you plug in 1, you will get 1 plus 1, 2 squared, 3 squared, and so on, which will basically give us the second part, right? So the second property of our convex polygon. So that's it. So all that we are left with now is to find a procedure to figure how to come up with these numbers in clockwise order, right? So or counterclockwise order, I should say. Okay, so let me equivalently express this as the sum from r is equal to 0 to 1989 of, by De Moivre, I can simplify this to epsilon to the rth power is equal to 0. So this follows directly from the lemma. Now the only thing remaining is to figure how to find the relevant permutation of these numbers here. So what permutation works? So it's all based on the fact that, so let me open another imagination box here. 1990 nicely factorized into 1999, which is a prime times 10, which is, so finally 2 times 5 times 1999. And as a result, consider the following. Let alpha be simply equal to epsilon, so which is the 1990th root of unity, to the raised to the power 10, or I should probably say 2 times 5, and then beta simply as epsilon to the power 2 times 199, and finally gamma equal to epsilon to the power 5 times 199. Notice here that, because epsilon is the 1990th root of unity here, if I raise, let's just another imagination. So all the right column I'm using just for my ideas here. Epsilon, if I raise it to the 1990th power, obviously that would give us CIS 2 pi over, using this, I should say, sorry for that, using this, so 1990 times 2 pi over 1990, so the 1990s will cancel out, so cosine 2 pi, which is 1, minus I times sine 2 pi, which is 0, so that would give us just 1, right? So as a result, what I'm claiming here is that alpha raised to, because it's missing a 199, alpha raised to 199th power, that's equal to 1, but in a similar way, beta raised to the 5th power will also give us 1, and as is gamma is missing a 2 here, raised to the 2nd power is also equal to 1. Obviously, you can say that gamma is actually equal to minus 1, but that's I prefer to stick with this notation. And if you will, we can also put them into the unit square, but that's all these alpha, beta, and gamma are located on the unit square. Unit circle, what am I saying here? I'm high. Okay, so if you have the unit circle, let me quickly show you where they are each located. So if epsilon is somewhere here, where this angle here is 2 pi over 1990, in reality it's much smaller angle, but okay, so that's epsilon. Then you have epsilon to the 10th power, it's a 10 rotation here, so here is epsilon to the 10th power, which happens to be alpha. Then you have epsilon to the 2 times 199th power, which is here. That's epsilon raised to the power 2 times 199, which is beta. And finally, epsilon raised, that's gamma basically. Epsilon raised to the 5 times 199. It's missing a 2 here, so if I square it, it already have an argument of 180 degrees. It will, the whole thing will become 360 degrees, but so the gamma is basically equal to minus 1 here on the unit circle. But anyhow, going back to our thing, because of this way of how we defined each of these, I realize I can make the following claim. So this implies that this is again a very well-known feature of complex numbers, and I don't want to lengthen this lecture, which is already getting very long. So I have sorry for that. I would have, this implies that 1 plus alpha plus all the way to alpha to the power 2, all the way to alpha to the power 198 is equal to 0. In a similar way, 1 plus beta square all the way to beta to the power 4 would be equal to 0. 1 plus gamma square. Yeah, oh shoot. Okay, because we have only so 1 plus gamma is just 0. Sorry for that. But the reasoning is clear, right? Because alpha is the root of the equation x to the power 199 is equal to 1, as a result, in a similar way, beta, and you can factorize this, what I would like to say. For instance, let me just show you an example. So alpha is the root of this expression here, minus 1 is equal to 0. But when you factorize this, you get x minus 1 times all this thing here, right? So okay, so how do we factorize this? I think it's this expression here, 1 plus x all the way to x to the power 198. So that thing is equal to 0, suggesting that either x is equal to 1, which is not the case, or this guy is equal to 1, which is, so you get the idea, is equal to 0, sorry. This guy is equal to, the whole thing has to be equal to 0. But anyhow, so these are some very well-known facts as well. Now let's begin the solution. We have enough I think background, or yeah. Okay, so now consider this set of triples. Let t is equal to, let me actually use a different color. So let t be the following triples, triples of integers in z cube, such that so we have 0 is less than or equal to j, strictly less than 199, 0 less than or equal to k, strictly less than 5, and 0 less than or equal to l, strictly less than 2. Well, that's our set. This is the set T. Obviously, T has a size. So here we have 199 numbers, 5 numbers here, and 2 more numbers. So you multiply them. You do 2 times 5 times 199. It has 1990 triples in it, and I will make use of the following observation now. So I have 2 observations. Observation 1, consider the following set. The set 10j plus 2k plus l, such that j, k, and l are in T. Now my question is, what is this set equal to? And let me give you a few. If you would like to, you can pause at this moment, because this is a very important observation. So I assume you guys paused it, and now the answer is this: 0, 1, all the way to 1989, and it's not too hard to see it, so you can try it, and you will see that all these numbers here are unique. Remember that the set T here has 1990 numbers. Each one of these are unique, and as a result, each of them will appear once in this set. So that's the first observation. The second observation is equally important, and probably warrants a proof, but I will just leave the proof to you as a homework, because the video is already getting so long. I claim that there's an alternative way to write this set, to sweep this set, and it is the following. So I claim that the remainders in mod, sorry for that, in mod 1990 for the following numbers. Now guess what? These numbers here, 2 times 5 times j plus 2 times 199 times k plus 5 times 199 times l. Again, j, k, l are triples. Triples from T. Again, guess what? What is this setting? Oh, well, obviously, I'm evaluating in mod 1990. And, well, if you pause the video for a moment, and you would be right. Yes, this is again equal to 1989. So at this moment, I need to, as an instructor, I would do it all the time, right? I would like to give this as a homework to you. So can you prove that this set sweeps all of this, right? So this definition here is basically equal to this set. The way to do it is obviously because T has 1990 elements in it. At most, we have 1990 numbers that we can generate. All you need to do is every number generated here is different, right? So two randomly picked numbers can never be equal to. If they are equal to, then you should then this should imply that they are taken from the same set T. They were generated by the same triple, basically. So it's not too hard to show that this is also equal. But then this gives us enough information to now construct this set that we have been struggling to do for a long time now. Here is a potential construction of the set of numbers. So construct the construction, let's say, of this set n0 n1. Recall and 1989 of this set, where you recall that which is a permutation of the numbers that we just said. So from 0 all the way to 1989, the integers of the set 0, 1 all the way to 1989. So here is the construction. If you want, you can pause the video again. Try to see if you can use observation 1 and 2 to come up with an idea on how to construct it. But here it is. Okay, so assume you guys have paused, and here is a way to construct it. So you have the two observations for given. So here is one for given R in the set 0. Okay, so let's write it 0, 1 all the way to 1989. Let the triple JKL in T be the one which would generate it as a remainder if we use this definition, the second observation, basically, right? For which this expression here will give the remainder R. So the expression here would give the, so for given R in this set, let this T be, let JKL in T, that this triple be such that, so 2 times 5 times J plus 2 times 199 times K plus 5 times 199 times L is congruent to R in mod 1990. So you find the unique JKL that would give that remainder. So once you have this JKL, so this was step 1. In step 2, you plug in those values of J, K, and L into the expression in the first result, right? So plug in JKL obtained in step 1 into this expression 10J plus 2K plus L to get an R, basically. Sorry for that. To find an R, and that's it. We claim we can build the set NR in this fashion in 2 steps, basically. Now all that is remaining is to show that these numbers work actually. So these numbers defined in the following manner, in this 2-step manner, will make the expression this expression here, yeah. So that they will in fact make this expression equal to 0. We need to prove that, right? So if they make equal to 0, so we have this permutation of numbers from 0 to 1989, and when plugged into the expression, so let's write that down. Now finally show that the summation for r is equal to 0 to 1989, 1 plus nr squared times ci, or let's just use the epsilon notation. I think we decided to call it epsilon r, is by de Moivre, right? So show this, right? So show that the nr satisfy the required condition if we can make, if the nr's ordered in counterclockwise in this fashion, in this order, for each r, you start from r is equal to 0, then 1, then 2, and so on, we should be able to generate the sides of our polygon. All that is remaining is to ensure that their vector sums is equal to 0, suggesting that the polygon closes, right? So you start as a vector at a point and then it closes the loop at that point, right? And for that, I will need one more observation, which is, again, I will just leave it as a homework, but it's again a tiny observation. But before I begin, consider the following expression. So epsilon to the r, so in this expression I have two parts in it, right? So let's consider epsilon to the r power first. Epsilon to the r power is equal to epsilon. Remember how I generated the r, right? So epsilon to the r power is equal to epsilon to the power 2 times 5 times j plus 2 times 199 times k plus 5 times 199 times l, and well because r is from the set 0 to 1989, obviously, right? So it will be, so this whole thing is congruent to r in mod 1990, but because after 1990 we are cycling on the unit circle, right? So once we reach 1990 we start all over again, so the angles will, okay, so but this thing is equal to, now going back to our alpha, beta, gamma notation somewhere here, yeah, I'll make use of these symbols now, obviously. So this is equal to epsilon to the power 2 times 5 times j times epsilon to the power 2 times 199 times k times epsilon 5 times 199 times L, but epsilon to the 2 times 5, so this one is basically alpha, so this is alpha to the jth power, then this guy is beta, so we have beta to the kth power, times finally this one is gamma, gamma to the lth power, and as r, recall that r is chosen from the set 0, 1, all the way to 1989, one by one. As we pick an r here, so as 0, 1, 2, 3, it will create the triples j, k, l, as we did in step 1 of the procedure above. So this will go through all the t's, it will and what's interesting is the following. So we would have, once everything is plugged in, now I have the expression. So this expression here, the left hand side, is equal to the summation, so 1 plus nr, we defined it as here, so it is 1 plus 10j plus 2k, so let's write that down, 1 plus 10j plus 2k plus l times, and the second part, this one, epsilon to the r power, is just this, alpha to the j, beta to the k, gamma to the l, okay, I can get rid of this, and this ranges across all j, k, l in t, right? So therefore the boundaries of the summation sign has changed now, because for each r we can uniquely find a triple in t that satisfy this. Now all that's remaining is to show that this product is equal to 0. But now when you, oh shoot, I forgot the square here, sorry for that. So there's a square here. Now the critical observation, the remaining final observation, is this: when I square this parenthesis here, what will come out is you will have at most 2 terms multiplying with each other. That's the critical thing. So you will never see, so let me open another imagination box. You will never see a term which have j to the power, I don't know, t k to the power l, t1, let's say t2, and then t2. Haha, that's fun. Okay, and l to the power t3. There will be no such expressions, right? All the expressions that I will have, so I will have 4 times 4, 16 terms. At most, I will have 2 different variables of the jkl, but not 3 of them will appear in the same expression. But this is important, because when that's the case, our summation will come out of things like this. So the summation will have, well, a function, let's say a function of j and k at most, right? And then it will have an alpha to the power j, beta to the power k, and then I should be able to take out the gamma to the power l outside the summation right side, right? So this will give me a summation of all the triples in T, and yeah. So gamma L. Okay. So this will not be T actually. It will be from L is equal from 0 to 1, right? But that guy we earlier, does that make sense? I'm kind of going through very fast here, but the thing is obvious, right? So you will have, we will trace out all the L's here. For every single L here, the gamma L will take all these values, and eventually I will be able to factor them out for each of these expressions. So, but hey, we already proved that yes, these are all equal to 0, right? So including this one, for instance, right? So that one will be simply equal to 0 here on this side. So it will vanish the whole term, plus, and then you will have, let's call it function jk. And then you will have another summation with function, let's say jl, the same thing, jl in terms of jl, and then you have alpha to the power j, and then gamma to the power l. But again, I will be able to factor out the beta to the power k, where k will range from 0 to 4. That thing will vanish, the whole product is 0 again, and so on. So you will never have terms where all 3 appear at the same time, but when that's the case, one of them will always be free. You will be able to always factor it out, and that will vanish the term. So every single one of them will be vanishing, as we said. And by the way, the single ones will also vanish, obviously. If the expression here, the function is in terms of only one variable, or even this one, like if in terms of a single one, then all these things are separable. You will be able to separate each one in the set T. So you will have each one separated. Like, for instance, let me give one more example. Yeah, sorry for that. This part is very sloppy, what I'm trying to explain. But you will get expressions like this, basically. So you'll have alpha ranging from j equals from 0 all the way to 1998, I guess, alpha to the power j, and then summation beta to the power k equals ranging from 0 to 4. Oops, sorry for that. And finally, gamma to the power l, l ranging from 0 to 1, sorry, but obviously every single one of them are already 0. So the worst case that can happen will have 2 terms. Okay, so long story short, this whole thing would have to be equal to actually 0, and that does the trick, right? So we have found a way to construct these numbers, n sub 0, n sub 1, n sub 99, such that they give this 9 results, this 9 left-hand side expression, make it equal to 0. They may, but then by the lemma that we proved at the very beginning, whenever that happens, it proves that our polygon is equiangular, and the side lengths are in the given order, right? So a given and basically this n sub r business here, the way we created each of these n sub r's, dictates how the side lengths will be ordered around the polygon on that given order, and basically that solves this very beautiful problem. Unfortunately, this was a little bit hard problem, requires a lot of background information, not only in geometry but also in number theory, and having a good sense. But as I said, this is a very nice problem, and hope you enjoyed it, and I'm looking forward to see you guys in our next video.